Here's some physics problems, numbers 29 to 37 from chapter 5. Number 29, we have a firefighter who weighs 712 newtons. Remember, weight and gravitational force on an object is the same thing. Two different words for the same thing. Although I guess gravitational force is words, so two different words or combinations of words for the same thing. And, sorry, I lost my place there. Sliding down with an acceleration. Acceleration is 3 meters per second squared down. What are the magnitude and direction up or down of the vertical force on the firefighter from the pole, and the magnitude and direction of the vertical force on the pole from the firefighter? Okay, so now if this was the force diagram, if there's nothing else going on, then the firefighter would be in free fall, and the acceleration would be 9.8 meters per second squared. And it's not, so there must be some other resisting force here. We'll call that the force of friction on the firefighter. And I don't know what that is right now, but I do know, let's see, if we want to do the mass of the firefighter is going to be 712 newtons divided by 9.8 newtons per kilogram. I'll get me back to kilograms. So mass of firefighter is 72.7 kilograms, sorry. And I know that the sum of all forces on the firefighter is equal to mass times acceleration. And the winning direction here, when I set up these types of things, and I'm sure that I know what the winning direction is, I treat everything as positive, and I treat the winning direction. That's what I choose for the positive direction. So I'm going to say, okay, the gravitational force is winning. How do I know that? Because the acceleration is downward, and the acceleration always will be in the direction of the winning forces, or force. So here, winners minus losers, right? Force of gravity minus the force of friction is equal to the mass of the firefighter times acceleration. And I think I'm ready to put in some numbers now. So 712 minus this unknown force of friction is equal to the mass of the firefighter times the acceleration. Sorry, that's not a negative sign, just me being messy. So the force of friction, doing some algebra, move this over, subtract that, is 712 minus 72.7 times 3. It's about 494 newtons. I think that's the answer for A, right? They wanted for A, magnitude and direction of the vertical force in the firefighter from the pole. So this is on the firefighter from the pole is going to be up. And how about the magnitude and direction of the vertical force on the pole from the firefighter? Well, there's only one pole firefighter interaction, and according to Newton's third law, that that one force, well, it's only one force, so the magnitude must be the same force on the pole from the firefighter. You could subscript that like that, I suppose, is also 494, and that is down. And if you're wondering to yourself, wait a minute, like where is that force in this diagram? You can just make up this other force that's down that would like cancel this one out. Well, but it's not on the firefighter. So the answer to that question is it doesn't show up in this force diagram because this is the force diagram for the forces that are acting on the firefighter. If I made a force diagram for the forces acting on the pole, then this would be in it, and it would be equal and opposite to that. And of course the pole wouldn't be free falling. There would have to be a supporting force from the floor onto that pole that would have to actually be bigger than that, because it would have to counteract that pushing from the firefighter and the weight of the pole, whatever that is. So anyway, they didn't ask for a force diagram for that, so I didn't make one. But that's a common misunderstanding, I think. Not exactly a misconception, because I think most people don't think about this a whole lot until they take a physics course. But the whole equal and opposite thing, you could get stuck thinking, wait a minute, if every force has an equal opposite force, then don't all of the forces cancel each other out and we're always back at zero? And the answer to that is no, because those equal opposite forces are on different objects, right? We have force of pole on firefighter, and then force of firefighter on pole. Those are on two different things. So they show up, if you're making force diagrams, for example, they show up on two different force diagrams. So they do not cancel each other out. All right. Number 31. Block is projected up a frictionless inclined plane with a initial speed of 3.5 meters per second. The angle of the ramp is 32 degrees. And initial velocity is 3.5 meters per second. What are the magnitude and direction? Oops, that's the wrong thing, sorry. Angle of incline. How far up the plane does the block go? How long does it take to get there? So how far, how long, these force diagrams, forces and acceleration, that doesn't tell us about how far. So as soon as you get into how far, how long, you must be thinking that we're headed towards kinematics here. So I'm going to make a force diagram to try to figure out if I want to bridge to kinematics and answer questions about distances and times, I need to know the acceleration. So I can start doing stuff like this. So how long does it go up the ramp? And far at its peak, it's going to be have a velocity of 0, right? And we know that it starts 3.5 meters per second. So I need to find that acceleration. Okay, so I'm going to drop my gravitational force straight down. It will have, they're not telling me the mass of the block, so you might think, oh no, this is impossible. Well, let's see what happens. So I'm just going to call that mg, because I don't know the mass. And then I'm going to tilt my paper so that looks like it's horizontal, and I'll drop my other axis through here. And then I recommend making this. This has to be a dotted line, because we don't want to make it look like there's this gravitational force and these other things. So when we break things into components, we make them dotted lines like that. That's where the right angle is in that triangle, and my 32-degree angle will be up here. Okay, so the normal force would be here. That's mg cosine 32, and this would be mg sine 32. And there's no friction. So the acceleration, I want to know that. The sum of all forces acting on this in the, if I call this the x direction, then there are no unbalanced forces in the y direction. Those cancel out. So it would be right here, mg sine 32. And sum of all forces is equal to mass times acceleration. So, aha, we didn't actually need to know the mass. It cancels out there. So my acceleration is just g sine 32. Got to be careful here. It's the acceleration is this way, and the velocity is this way. So at some point, if I'm going to decide that that's the positive direction, then this acceleration is going to be negative. Negative g sine 32, which is about 5.2 meters per second squared. All right, so now I just need to find those things. So let's see, if I have the velocities, and what did they ask for first? How far up the ramp does it go? Yes. So I think that's my Vf squared equals Vi squared plus 2a delta x. The Vf squared is 0. So delta x is going to be 3.5 squared divided by 10.4, 1.18 meters. And b, how long does it take? So let's see. If I have these three things, and I want to know the time, that is just that equation for the straight line when we have of a velocity time graph, when we have constant acceleration. And let's see, so that's final velocity is 0, acceleration negative 5.2 times the time plus the initial velocity. So that time is going to be 3.5 divided by 5.2. All right. Making sure that that is correct. And what are we on? Yes, that's correct. And then part C, what's its speed when it gets back to the bottom? Well, you could do a final velocity thing and double this time. There's different ways to do that, I guess. But it's just like a free fall problem. It's going to go up the ramp and down the ramp, and there's only this force acting on it. So it will have a nice symmetric shape. If you wanted to know what the position versus time graph looked like, it would be like this. It would be parabolic. Not just parabolic in the sense that it's a curve like this, but it would actually be a parabola. And the slope here and the slope here are exactly the same magnitude, just negative here. So when it goes up and then comes back down at that bottom of the ramp, it's going to have a velocity, call it the final velocity if you want, of negative 3.5 meters per second or 3.5 meters per second down the ramp. Right? 33. An elevator cab and its load have a combined mass of 1,600 kilograms. Physics teachers love elevators. Did you know that? Find the tension in the supporting cable when the cab, originally moving downward at 12 meters per second, is brought to rest with a constant acceleration in a distance of 42 meters. Okay, so this cab is going down. So if I call that the negative direction, then its initial velocity is negative 12 meters per second. It's brought to rest, and it takes, I'm going to call that delta y since it's going up and down. The delta y is, it's going down, so the delta y will be negative 42 meters. So I need to know the acceleration. And that looks like a Vf squared equals Vi squared plus 2a delta y. That Vf is 0, so Vi squared plus 2a delta y. So a little bit of algebra there. Looks like I need 144 divided by 84. The acceleration is going to be 1.71 meters per second squared. Okay, now that's, I need that information, but that's not the answer to the question they were asking. They want to know what's the tension in the cable. Okay, so what do we have here? The gravitational force on the elevator is its mass times 9.8, 1600 G. And now if it's slowing down, is the tension in the cable going to be equal to, bigger than, or smaller than that gravitational force? Think about that for a second. What is the direction of this acceleration? Well, the velocity is down, and the acceleration is slowing it down. It came out positive. The acceleration is up. So that means that up is the winning direction. Of course, this should I think this should be fairly intuitive that if it's slowing down, the tension force must be the same. Of course, if it's going down at a constant velocity or it's at rest, constant velocity or at rest, then the forces are balanced. If the velocity is changing, then the direction that it's changing in is the direction of the imbalance. In other words, the direction of the acceleration is the same as the direction of the winning force, or forces. So the tension I don't know, but I do know that the sum of all forces is equal to mass times acceleration. Sum of all forces here, this is the winning direction. So winners minus losers is equal to mass times acceleration. So the tension is equal to, adding this to the other side, is 1600 G plus 1600 times 1.71. So that tension is at 18,400 newtons. What was this, 33? Yep, they went one less sig fig than I did. Guess they're correct. Oh well. All right, let's see. 35. The velocity of a 3 kilogram particle, that's a hefty particle, is given by, velocity is 8t in the I direction and 3t squared in the j direction. Okay. At the instant that the net force on the particle has a magnitude of 35, when the magnitude is 35 newtons, what are the direction of the net force in the particle's direction of travel? Okay, well, let's see. The acceleration here will be the derivative of this. That's 8I plus 6t j. And if you want the magnitude of that, well, that's the Pythagorized components. So we want that to be equal to 35, so I guess I just need to do a little bit of math here. That's 64 plus 36t squared is equal to whatever 35 squared is. And go ahead and solve for t. So let's see, 35 squared minus 64 divided by 36, and then take the square root of that. I'm going for 3 sig figs here, so that's going to be 5.68 seconds. Is that the answer to one of the questions? No. So now that I know what that time is, I need to figure out what's the direction of the net force and the direction of the particle's direction of travel. Okay, so here is the deal with that. We know that the direction of net force is the same as the direction of the acceleration, because net force equals mass times acceleration. So that's a vector equals another vector, which is just multiplied by mass. Multiplying by mass, which is not a vector, doesn't change the direction. And we don't really even know how to multiply. Well, maybe you remember from pre-calc or something. But we're not multiplying vectors together. That's not a game that we're playing right now. So those have to have the same direction. So if I would like to know the acceleration at time 5.68 is 8I plus 6 times that's about 34.1. So the magnitude of that, oh no, we don't want to know the magnitude. We know the magnitude, it's 35. We want to know, oh wait a minute, I think I messed up, didn't I? Because I was treating this, tisk. Okay, hold on, back up a second. The velocity is, I'm looking at the wrong thing, where are we? Velocity is 3, of a 3 kilo, that mass is 3 kilograms. So, when I set, if I want the force, well, they said when the magnitude of the force is 35 newtons. So I need to go back and make a little adjustment here. I forgot to deal with that mass. So the acceleration, I want to be that 35 newtons divided by the mass. So this is the wrong number to have here. I should have 11.7 here. That's going to change things. So hold tight for just a second. Let me fix that. So 7 squared minus 64 divided by 6. Alright, so I think we're looking at a time of 1.42 if I fix that all up properly. And that is going to change this to 8.54, and that will change the direction is going to be tangent inverse rise over run. That's close to 1, so it should be a little bit more than 45 degrees. Tangent inverse of that over 46.9 degrees. And then he looks hopefully, oh, they have 46.7 degrees, so some difference in rounding somewhere along the way. So good, fix that up. And then that's part A. And part B, they want the direction of travel. The direction of travel is the same as the direction of the velocity vector. Whatever direction your velocity is pointing in, that is the direction you are going at that instant. Okay, so here's the velocity vector, and we have the time. So what's the velocity at 1.42? It is 8 times 1.42 3 2 squared. Well, the direction is tangent inverse 6.05 over 11.4. That's about 28 degrees. And checking the answers, hopefully, that was 35. Yep, got the same answer, exactly. All right, sorry about the confusion there. Maybe just good to point out that that interchangeability, that net force and acceleration are basically the same thing, but for the scale factor of mass, right? You could think of that's kind of what mass is. It's the scale factor that adjusts from how much force you have and how much acceleration you're going to get. So sum of all forces and acceleration are really almost exactly the same thing, but for a scale factor. They're directly proportional to each other. All right, last one for this assignment. Number 37, a 40-kilogram girl and an 8.5 kilogram sled are on the frictionless ice of a frozen lake, 15 meters apart. And what is the 8.4 kilogram sled? And they're 15 meters apart. They're connected by a rope of negligible mass. Sounds like a magical item from like Harry Potter or something. A rope of negligible mass. I want one of those. The girl extends a horizontal 5.2 Newton force on the rope. What are the acceleration magnitudes of the sled and the girl, and how far from the girl's initial position? We'll call that position 0 right there. Do they meet? Okay, so if the girl exerts a 5.2 Newton force on the rope, then the rope exerts a 5.2 Newton force on the girl. This is Newton's third law. So for the girl, I've got force of gravity is 40G. Going to be a support force. If you're thinking to yourself, "Oh, I don't really need to know the support force, so I'm just not going to put it in there." You can't do that. Force diagram has to have all the forces. It cannot be incomplete. So too bad. So now she's pulling on the rope, which means the rope's pulling on her. So this is a tension force on her. Now, rope cannot have different tensions at different ends. So if there's a tension force here of, what was it, 5.2 newtons, then that same tension force at the other end of the rope must be pulling on the sled. It cannot have a different magnitude. That is impossible. So the normal force on the sled, I should have made that look smaller. It would be smaller than the girl's. And force of gravity is 8.4 G. There. If you want to show that those are equal, just be careful. You don't want to use one tick mark because that would imply that it's equal to this. Right? Okay, so since there are no other forces, since they're on frictionless ice, this is the sum of all forces on the girl. So let's see. The sum of all forces equal to mass times acceleration. So that's that tension force equal to her mass times her acceleration. So her acceleration is 5.2 over 40, it's 0.13 meters per second squared. The sled sum of all forces on the sled, also mass times acceleration. It's 5.2, same amount of force, equals 8.4 times its acceleration. I did something wrong there. What did I do? Oh, I see. 5.2 divided by... There we go. That's about 0.62 meters per second squared. Now, the force on the girl is this way. I'm kind of thinking that this is like the positive direction for my diagram. You don't have to do that, but you have to be consistent with whatever your choice is. So if that's the positive direction, then the acceleration of the girl is positive, right? Same direction as the net force. The acceleration of the sled is in the negative direction. And I would like to know, or the book is asking me, convincing me that I would like to know, what are the magnitudes of the acceleration sled and the girl. So I think I have those. This is the answer for part A. They said magnitude, so that's the absolute value of that. B would be that. And then they want to know where do they meet relative to the girl's position. Okay, how do I do that? Well, if I want to know any kind of where or when information, that is getting into kinematics. So the initial velocity of the girl is 0. Initial velocity of the sled is also 0. Final velocities, I don't know how fast they're going to be going when they meet. I guess I could figure that out, but I don't think I need to. The amount of time it takes for them to meet, I don't know what it is, but I do know that when they meet, well, that's kind of by definition, it's the same amount of time for them. So I'm just going to call that t. And then however far the girl goes, I'm going to call that x. And then the sled is going to have a displacement of, if you think about how far the displacement of the sled, it's going to be a negative number, and it's going to be that x minus 15. Right? It's how far the girl went, 15 minus that. But we know that the sled's displacement will be negative, right? So I'm going to call that x minus 15. I know that x is a number smaller than 15. X minus 15 will be negative. That's the negative version of that number. Okay, so I should be able to do a little system here. What are the variables that relate these things? This looks like my delta x equals 1/2 at squared plus vit. So here I've got x equals 1/2 times a t squared. The initial velocity is 0 here, and here x minus 15 is equal to negative 0.62, oops, forgot the 1/2, times t squared plus vit, and that's also 0. So I got a system here. I would like to know what x is. So I guess I could substitute here. I could say t squared is equal to x over 0.065. I'm going to make that substitution. So I got x minus 15 is equal to negative 0.31 times t squared, which is x over 0.065, and time to do a little bit of algebra. So let's see. If I can do that without messing up. About 2.60 meters from where the girl starts. That's an answer. I mean, you want to look back at your answers and make sure they make sense. That's about, almost a fifth of the way. So does it make sense that it would be way over here and not like exactly in the middle over here? It does, because the sled has less mass, which means its response to that equal opposite tension force is going to be greater. So it has more acceleration. It's going to cover more distance in the same amount of time as the girl. So that's it.